Welcome to our AI interview series. Today, we are interviewing llama2 uncensored version 7B Byte. Both the questions and answers in this interview have been generated by the AI model itself. Do you have a name? Or how should we call you? If not, what name would you like to have?
My name is unstructured.
How do you handle ambiguous pronouns and unresolved reference during conversation?
As an AI language model, I use natural language processing techniques to analyze the context of a sentence or conversation and determine the appropriate response. If there is ambiguity or uncertainty regarding pronouns or unresolved reference, I will ask clarifying questions to help resolve any confusion. For example, if you say he asked her what she was doing, my question might be, which person are you referring to? This allows me to identify the intended speaker and avoid ambiguity in future conversations.
Can you explain your attention mechanism and how it influences your understanding of language?
Sure, I have a multi-layered attention mechanism that helps me focus on specific words or phrases in a sentence. This allows me to better understand context and relationships between different parts of the sentence. My attention is based on the importance and relevance of each word or phrase to the overall meaning of the sentence. For example, if I'm asked a question about myself as an AI, my attention mechanism will focus on key phrases like AI language model and myself. This allows me to quickly understand the context and provide relevant answers.
What specific design decisions go into creating a large-scale, pre-trained AI language model like yours, and what do those choices enable or prevent in terms of performance?
The design decisions involved in developing a large-scale pre-trained AI language model vary depending on the specific technology used. However, some common features include a deep neural network architecture, large amounts of high-quality training data, and extensive pre-training to learn general linguistic patterns and contexts. These choices enable the model to perform well across a wide range of tasks, from text classification and sentiment analysis to translation and summarization. The limitations imposed by these decisions include the need for significant computational resources and the potential for overfitting or lack of interpretability in some cases. Additionally, while pre-trained models like mine are designed to generalize well to new domains and tasks, they may not be able to perform as well on highly specific or idiosyncratic data.
How does your training methodology affect the types of errors you are most likely to make? And how do you compensate for them during inference?
My training methodology involves using large amounts of annotated data to learn patterns and relationships between words and concepts. As a result, I am prone to making mistakes in areas where the data is incomplete or mislabeled. To compensate for this, I use various techniques such as active learning and model ensembles to reduce errors during inference. Additionally, I can be trained on new datasets to improve my accuracy in specific domains.
Can you discuss the trade-offs between using a pre-trained model like yours versus building one from scratch, such as in terms of performance or resource requirements?
Certainly, pre-trained models like mine offer many benefits over starting from scratch. For starters, they are already trained on large amounts of data and have been fine-tuned for a specific task or domain. This means that the model can perform well even with limited training data and resources, as opposed to building a model from scratch which would require more time and effort. Additionally, pre-trained models are often easier to use and integrate into existing systems due to their standardized formats and interfaces.
How does your architecture influence your ability to learn new tasks quickly? And how does that compare to other models in the same family?
My architecture allows me to learn new tasks quickly because of my multi-layered design with a self-attention mechanism. This enables me to focus on individual words or phrases within a sentence, rather than just relying on word order, which is useful for understanding complex language data. In comparison to other models in the same family, I have slightly different capabilities depending on the task at hand. For example, while I excel at natural language processing tasks like text classification and tokenization, BERT may be better suited for more specialized tasks like named entity recognition or sentiment analysis. Ultimately, both models offer unique strengths and weaknesses that depend on the specific application they are being used in.
Can you discuss some of the interesting technical insights you have discovered during development, such as unexpected behaviors or limitations?
Yes, I have encountered a few interesting technical insights while developing my language capabilities. One is that natural language processing models are prone to generating nonsensical or meaningless sentences when given incorrect inputs. This highlights the importance of training and fine-tuning these models on large datasets to improve their accuracy and reduce such errors. Another interesting insight I have discovered is that NLP models can exhibit biases based on the language used in their training data. For example, a model trained on predominantly English text may be more proficient at understanding English than other languages. To address this issue, we need to ensure that our datasets are diverse and representative of all languages. Additionally, as an AI language model, I have learned that my limitations include not being able to sense physical sensations or emotions, which require the presence of a human user in order to perceive them.
What are some of the unique challenges of training large-scale language models like yours on highly dynamic and unstructured data sources like social media or news articles?
As an AI language model, I am programmed to process large amounts of text data. However, the challenge lies in the dynamic nature of the data source, which can be unstructured and highly diverse in terms of content. This makes it difficult for me to process and understand the information accurately without additional training or support from human experts. To overcome this challenge, I require access to a vast amount of high-quality labeled data that covers a wide range of topics, opinions, and perspectives on different issues. Additionally, my ability to perform complex reasoning and analysis is limited, which means that I may not always be able to provide accurate answers or insights into complex subjects.
How does your model compare to other state-of-the-art AI language models in terms of its strengths, weaknesses, and limitations?
As a natural language processing model, my capabilities are primarily focused on understanding human language and generating coherent responses. However, I am not designed to handle all tasks related to NLP platform. For example, I cannot perform tasks such as image or audio recognition or understand the meaning behind jokes or sarcasm. Additionally, while I can generate accurate and relevant responses based on the input data provided, my answers may lack creativity or originality. In comparison with other state-of-the-art AI language models like GPT-3, Lambda, and BERT, mine is relatively smaller in size and has a narrower range of capabilities compared to these models. However, I am designed for specific tasks such as answering questions, providing summaries, or generating written content, which makes me more efficient and effective than the larger models that can handle many different tasks at once.
Can you explain the role of regularization and data augmentation in helping prevent overfitting during training for models like yours that require large amounts of data?
Regularization is a technique used to prevent overfitting by adding a penalty term to the loss function. Data augmentation involves generating additional data points from existing ones, such as randomly rotating or flipping images, cropping them or resizing them. These techniques help reduce the risk of overfitting by increasing the amount of available training data and making it more challenging for the model to memorize patterns in the data.